Based on its appearance in visible light, the Andromeda Galaxy is classified as an S B galaxy in the de Vaucouleurs-Sandage extended classification system of spiral galaxies. However, infrared data from the 2 Mass Survey and the Spitzer Space Telescope showed that Andromeda is actually a barred spiral galaxy, like the Milky Way, with Andromeda's bar major axis oriented 55 degrees anti-clockwise from the disk major axis. There are various methods used in astronomy in defining the size of a galaxy, and each method can yield different results concerning one another. The most commonly employed is the D25 standard, the isophote where the photometric brightness of a galaxy in the B-band, 445 nanometers wavelength of light, in the blue part of the visible spectrum, reaches 25 mag/arcsec2. The third reference catalog of bright galaxies, RC3, used this standard for Andromeda in 1991, yielding an isophotal diameter of 56 kiloparsecs, 152,000 light-years, at a distance of 2.5 million light-years. An earlier estimate from 1981 gave a diameter for Andromeda at 54 kiloparsecs, 176,000 light-years. A study in 2005 by the Keck telescopes shows the existence of a tenuous sprinkle of stars, or galactic halo, extending outward from the galaxy. The stars in this halo behave differently from the ones in Andromeda's main galactic disk, where they show rather disorganized orbital motions as opposed to the stars in the main disk having more orderly orbits and uniform velocities of 200 km per second. This diffuse halo extends outwards away from Andromeda's main disk with the diameter of 67.45 kiloparsecs, 220,000 light-years. The galaxy is inclined an estimated 77 degrees relative to Earth, where an angle of 90 degrees would be edge-on. Analysis of the cross-sectional shape of the galaxy appears to demonstrate a pronounced S-shaped warp, rather than just a flat disk. A possible cause of such a warp could be gravitational interaction with the satellite galaxies near the Andromeda Galaxy. The galaxy M33 could be responsible for some warp in Andromeda's arms, though more precise distances and radial velocities are required. Quote, spectroscopic studies have provided detailed measurements of the rotational velocity of the Andromeda Galaxy as a function of radial distance from the core. The rotational velocity has a maximum value of 225 km per second, 140 miles per second, at 1,300 light-years, 82 million astronomical units, from the core, and it has its minimum possibly as low as 50 km per second, 31 miles per second, at 7,000 light-years, 440 million astronomical units, from the core. Further out, rotational velocity rises out to a radius of 33,000 light-years. 1 times 109 astronomical units, where it reaches a peak of 250 km per second, 160 miles per second. The velocities slowly decline beyond that distance, dropping to around 200 km per second, 120 miles per second, at 80,000 light-years. 1 times 109 astronomical units. These velocity measurements imply a concentrated mass of about 6 times 109 m in the nucleus. The total mass of the galaxy increases linearly out to 45,000 light-years. 8 times 109 astronomical units. Then more slowly beyond that radius. The spiral arms of the Andromeda Galaxy are outlined by a series of HII regions, first studied in great detail by Walter Baade and described by him as resembling beads on a string. His studies show 2 spiral arms that appear to be tightly wound, although they are more widely spaced than in our galaxy. His descriptions of the spiral structure as each arm crosses the major axis of the Andromeda Galaxy, are as follows: section pp 1062, section pp 92. Since the Andromeda Galaxy is seen close to edge-on, it is difficult to study its spiral structure. Rectified images of the galaxy seem to show a fairly normal spiral galaxy, exhibiting two continuous trailing arms that are separated from each other by a minimum of about 13,000 light-years, 820 million astronomical units, and that can be followed outward from a distance of roughly 1,600 light-years, 100 million astronomical units, from the core. Alternative spiral structures have been proposed, such as a single spiral arm or a flocculent pattern of long, filamentary, and thick spiral arms. The most likely cause of the distortions of the spiral pattern is thought to be interaction with galaxy satellites M32 and M110. This can be seen by the displacement of the neutral hydrogen clouds from the stars. In 1998, images from the European Space Agency's Infrared Space Observatory demonstrated that the overall form of the Andromeda Galaxy may be transitioning into a ring galaxy. The gas and dust within the galaxy are generally formed into several overlapping rings, with a particularly prominent ring formed at a radius of 32,000 light-years, 9.8 kpc, from the core. Nicknamed by some astronomers the Ring of Fire. This ring is hidden from visible light images of the galaxy because it is composed primarily of cold dust, and most of the star formation that is taking place in the Andromeda Galaxy is concentrated there. Later studies with the help of the Spitzer Space Telescope showed how the Andromeda Galaxy's spiral structure in the infrared appears to be composed of two spiral arms that emerge from a central bar and continue beyond the large ring mentioned above. Those arms, however, are not continuous and have a segmented structure. Close examination of the inner region of the Andromeda Galaxy with the same telescope also showed a smaller dust ring that is believed to have been caused by the interaction with M32 more than 200 million years ago. Simulations show that the smaller galaxy passed through the disk of the Andromeda Galaxy along the latter's polar axis. This collision stripped more than half the mass from the smaller M32 and created the ring structures in Andromeda. Quote, "It is the coexistence of the long-known large ring-like feature in the gas of Messier 31, together with this newly discovered inner ring-like structure, offset from the barycenter, that suggested a nearly head-on collision with the satellite M32, a milder version of the cartwheel encounter." Studies of the extended halo of the Andromeda Galaxy show that it is roughly comparable to that of the Milky Way, with stars in the halo being generally metal-poor, and increasingly so with greater distance. This evidence indicates that the two galaxies have followed similar evolutionary paths. They are likely to have accreted and assimilated about 100 to 200 low-mass galaxies during the past 12 billion years. The stars in the extended halos of the Andromeda Galaxy and the Milky Way may extend nearly one-third the distance separating the two galaxies.